So yesterday at the end of the day, we were actually working on this elevator problem. Okay? And I said that elevator problems are a pretty classic Newton's second law, or at least introductory Newton's second law problem. Okay? There's some vectors, but it's forward and backward or up and down for an elevator. Okay? So they're not like terribly mathematically involved, but how they work is important. Okay? In the one we did yesterday, okay, we had 6,500 newtons of force acting up. Okay? What force was acting down? Gravity. Gravity was acting down. Okay? And we were able to calculate the force of gravity because we actually have a formula for it on our formula sheet. M times G. So we simply went 600 kilograms times 9.81, 9.81, okay, and we got 5,886 newtons. Okay, so now if we look at that and we say, all right, this is kind of a free body diagram, which is something we're supposed to draw. Okay, this is 600 kilograms, and it's being pulled upwards by 6,500 newtons, and gravity is pulling down with 5,886 newtons. This elevator is doing what? Mark, what's the elevator doing?
Going up.
Going up. Constant velocity or accelerating?
Constant.
It's the trickier question for sure. Okay, so remember, Newton's first law says you travel at a constant velocity if the net force is what number?
0.
0. Okay, in this situation, the net force is, well, I got 6,500 up, I've got 5,886 down, I got 614 newtons acting up. So this elevator is accelerating up. Okay, not just moving up, it is moving up, but it's also accelerating upwards. Okay, could I calculate the acceleration now that I know the net force? Okay, and that's what we ended off with yesterday. We said A equals F net, okay, divided by, actually we said F net equals the sum of all forces and M times A. Well, what we just did was the vector sum of all forces. 6,500 newtons up, 5,886 down for a total of 614 up. Okay, now that I know my sum of all forces is 614 newtons, and that equals M times A, and I know M, it's not hard for me to go about getting the acceleration. Every Newton's second law problem that you do is going to involve you doing those two things. Okay? Even if it says, here's the net force, well, then you got the vector sum of all forces. Okay? But it's still part of it. So, once I've done the vector sum of all forces, now I can find the acceleration. Sometimes the question will give you the mass and the acceleration and maybe 3 out of the 4 forces that are acting on it. You're going to have to determine what the remaining force is, what the missing force is. Okay? But it's always going to be the same two things. I'm going to do M times A and vector sum of all forces. Sometimes in different orders. Okay? But all Newton's second law problems break down to those two things. This is always the trickiest part, okay? Because that involves that visualization of the situation. All right, with that reviewed, I want you to try question number 1. It's the same elevator. Okay, so the elevator's mass is still 600 kilograms. Okay, the situation has now changed. I want you to calculate the acceleration of the elevator now. All right. We treat this one just like we did the last one. It's still an elevator question, and it's still a Newton's second law problem. Right? So I'm going to put in here that I have a 600 kilogram elevator. Okay? Now, the tension in the cable is 5,200 newtons. So my force upwards is 5,200 newtons. Okay? My force downwards, is that still gravity? So is it still the same number it was in the last question? It is, okay? So I'm just going to go Fg equals M times G, and I'm going to go 600 times 9.81, and now I've got 5,886 newtons down. Now I look at this situation, and I see that there's more force downwards than there is upwards, okay? Around 686 newtons to be exact. Okay, because if I go F net is the vector sum of all forces, I'm gonna say negative 5,886 plus 5,200, and I'm gonna get negative 686 newtons, or 686 newtons down. So now that I know that, can I find the acceleration? Right, did I just do the vector sum of all forces part? I did. Right, now I can do the F equals m times a part. I know what F net is, so I just need to divide by the mass, and I'll have the acceleration. 686 divided by 600 kilograms, okay, is 1.14 meters per second squared down. Okay, now, sometimes people look at this question and they get a little bit confused, because in this question, it asks for the acceleration of the person, not the elevator. Does it matter? It better not. Okay? The person in that elevator had better accelerate at the same rate as the elevator, or they are going to be in real trouble. Okay? They are going to be bouncing around off the walls and ceiling and floor inside that elevator if they don't have the same acceleration of the elevator. Okay? So they do. Right? They do not have a different acceleration than the elevator. They are a system, and the two parts must accelerate together. Something we'll talk about later in class today is systems, and how all the parts of a system have to have the same acceleration because they're connected. Okay? All right, I'm gonna have you guys do a few kind of practice problems here with just some entry-level stuff like we've been working on before I start throwing in heavily vectored questions, okay, or system questions where there's lots of other forces going on. Kind of get your feet under you first, okay, before I give you a push for anything else. Okay, so in your digital workbook, okay, this is the first page of the Unit 2 digital workbook. All right, I would like you guys to do number 5. Number 7. Number 12 and number 13. Okay, now, in some of these questions, you are going to have to use your acceleration formulas from last unit. Okay, if force is mass times acceleration, sometimes I might give you the kinematics information to get the acceleration first.
makes sense, because that's probably when we would eventually got online.
Mhm.
And we could just tweak sources, and then it just, I think he was working offline, is what I
Yeah,
think.
and then he shut it down and didn't.
Yeah.
I'd show that one to him, if they ever show up.
Yeah, no kidding, eh? Thanks, man.
Your speed's not changing very much, you're going from 0 to 3. You get a small acceleration. Yeah. What's that? Gotcha. Yes, tension is the cable pulling up. Whenever you have something that you're pulling on, it's how tight the cable is the tension. Yeah.
Okay, let's have a look at 13. All right, so one of the best ideas, and it's a great idea for any Newton's second law question, is to draw a free body diagram. Okay, so for this elevator question, all right, I've got a 1,200 kilogram elevator. Okay, and I know that it is accelerating. I'm putting acceleration over here because it's not part of the forces, so I don't put it on my free body diagram. Okay, but I'm told that the acceleration is 1.05 meters per second squared up. Okay, now that's what they tell me. That's really it. They want me to calculate how much force, we call that force tension, okay, because anytime you have a rope or a cable, it's tight when you pull on it, so the tightness of the cable is the tension, okay? They want me to find the tension in the cable, all right? Is there another force acting on the elevator? What other force is acting on the elevator? Gravity, okay? It has to be. I mean, the elevators are always affected by gravity. So the other force is this force. Can I calculate that force right now? I can, because I know the mass of the elevator. All right, so I'm going to go m times g, which is 1,200, okay, times 9.81, which I believe is going to be 11,776. 78? 72, 11,772 newtons. Okay, so now I know how much force is acting downwards. Let me ask you this. In a Newton's second law question, are these two things true? They're always true. Every Newton's second law problem, those two things are true. Do I have mass and acceleration already? Yeah, this is backwards. Okay, the question we did on the board wanted the acceleration. It gave me both forces. This one's giving me the acceleration, wants me to work backward to find the missing force. The method is almost exactly the same, except done in reverse. I'm going to do sum of all forces last and m times a first. Okay, because that's what I have right now. I have mass and I have acceleration. So I'm going to find my net force. Okay, and I'm just going to go 1,200 times 1.05. Okay, so my net force is 1,260 newtons acceleration was up, my net force has to be up. Okay, now the other way to arrive at that number is to add the two forces acting on the elevator together, agreed? Vector add them, so one would be negative. Do I know one out of the two already? I already calculated gravity, right? So I can also say then, if this is true, I can say that 1,260 newtons equals the force of gravity plus that tensional force they want me to find. And I already know the force of gravity. So if I want to find the tensional force, I'm going to subtract the force of gravity over to the other side. Okay, so I'll have 1,260 newtons, my F net, minus Fg equals the tensional force. So that's 1,260 minus, and here's the kicker, negative 11,772 newtons. Okay, vector sum of all forces. That force is down. Okay, so when I do that, I get 1.30 times 10 to the 4 newtons. Which kind of makes sense. That force has to be greater than gravity, otherwise the elevator's not going upwards. Agreed? So mathematically, not a challenging question, but because I asked it in reverse, it's suddenly different. Right? So like if we don't write everything down, and we don't do a good job of visualizing, we can miss that little detail that allows us to go, oh, that's just a question flip. Okay? Now, what is different in part B?
Wouldn't that be the answer to part B that you just did? Yeah.
Oh, sorry, A is downward. Nobody told me, nobody caught that. I just did part B. That's part B. What I just did, where it's accelerating upward. Okay, how is part A different? It's accelerating downward. Okay, so now this number here that I calculated isn't up, it's down, because it's the same acceleration. Okay, so now I do exactly the same thing I did right here, except now I make that negative, because it's down, right? Which means I'm going to get a different number. Okay, obviously the cable can't be pulling harder than gravity to make it go down. It has to pull less than gravity to make it go down. Okay, good catch, Lincoln. So when I do that one, okay, I'll have negative 1,260 minus negative 11,772. Okay, and I get 1.05 times 10 to the 4 newtons up. Still have to pull up. I'm essentially lowering the elevator. Okay, you don't just go ah, and let go. Okay, I mean that lowers the elevator, but it kind of does it at a very undesirable rate. Okay, I mean if you've ever lowered something over the side of a building, you still pull up on it to lower it. Okay, you're not pushing down on it to lower it. Okay, you still pull up against gravity. Everyone all right with that? If that's not something you understand, never go mountain climbing or rappelling. Okay? That's a really important understanding to have if you're belaying somebody. Okay? All right, now the real trick, the one that gets people, especially if I ask it on a test, is part C. You've already done all the math required to do this question, but it throws people off. What are the two key words in that question?
Constant velocity.
Constant velocity. What is the acceleration of an object traveling at a constant velocity?
0.
Right. What's the net force acting on an object traveling at a constant velocity?
0.
0. Right? We learned that the other day. Okay? That's Newton's first law. An object with no net force acting on it will continue to travel at a constant velocity unless acted upon by a net force or an unbalanced force. So if the object is traveling at a constant velocity, the net force is 0. That means gravity and tension are equal. That way they add up to 0. One is down, the other is up. Okay, that's a question I love throwing on the test. Okay, because it requires no math. It is strictly an understanding question. Okay, but it can, you know, people will start trying to do a lot of math, a lot of proof. Okay, when they don't have to. Okay, everybody kind of follow me on that one? Okay. Let's have a look at, actually, I'll give you about a 4-minute break here, and then I'm going to show you a couple of other types of questions as well.
Mr. Codere,
Mhm.
can I go to the bathroom?
You can. Okay. It's another one that's, you know, we have to pay close attention to the context of this question. All right, so you're traveling along in your car at 24 meters per second east. Okay, so writing down our givens here is important. We haven't even got to the free body diagram yet. Okay, but 24.0 meters per second east. Okay, when you slam on your brakes, right, the force of friction on your car tires is 1.8 times 10 to the 4 newtons. Okay, well that's a force, so that's got to go in my free body diagram somewhere. All right, so if that is my car, whose mass is the next thing they tell me, 1,500 kilograms, okay, and I'm going to say that direction is east, okay, where should I draw friction on that diagram? My car's traveling east. When I slam on the brakes, I do what? I slow down. Okay, so if I'm traveling east, my acceleration after I slam on the brakes is which direction? West. Okay, so when I slam on my brakes, what force am I using to stop my car? That's a trickier one. Friction. All kinds of it, but in general, friction. Okay, there's friction between your brake discs and the rotor. Okay, so you've got like your brake pads and the rotor. Okay, your brake pads squeeze on the rotor, they create friction, they create heat, and they slow the spinning of your wheel. Okay, if you lock them up, then there's the friction between the tires and the road. Even when you don't lock them up, there's still a friction between the tires and the road. As we know, when it gets icy, there's less of that, and we don't stop nearly as quickly. Okay, it is friction that slows you down when you slam on your brakes. So friction would go here. And it would be 1.8 times 10 to the 4 newtons. That's kind of what makes this question trickier, at least the first time you encounter a slam on the brakes question. Okay. Now, how far do you skid before stopping? What did they inadvertently tell me there?
Final velocity.
Right. Okay, they want me to find how far do I go before I stop. What else do I need to get that?
Acceleration.
Yeah, I need the acceleration. Now, since we know this is a Newton's second law type of question, we know that that formula applies. But right now, it doesn't look like we have enough information. We have the mass of the car, but we don't have the net force. Or do we? Let me ask you this. If I'm on a level road and I slam on my brakes, is my engine propelling me forward anymore? Do I have any forces going forward if I've slammed on my brakes? I sure hope not, otherwise I'm not going to stop very fast. Okay? So if I slam on the brakes and I'm on a level road, right, we'd have normal force and gravity, but we wouldn't even bother to write them because the car's not moving vertically. That's the only force acting on my vehicle that's not balanced. In other words, it's my F net. Okay? When you slam on the brakes, provided you're on a level surface, friction is the net force. Nothing else is acting on your car that's not balanced. Gravity and normal force are already balanced. Okay? So, I do know my net force. Okay, well, there's the vector sum of all forces part of that problem. I just had to identify that that was the only force acting on the car that wasn't balanced. Now, I know this number and that number, I can find A. Okay? It's a contextually difficult question. There's only 2 bits of math here. Right? I find A by going 18,000 newtons divided by 1,500 kilograms. All right, so the acceleration is going to be 12 meters per second squared. That's not unreasonable. If you slam on the brakes, you will be thrown into your seatbelt pretty hard, okay? And probably more than 1 G. You'll feel that. Okay, so 12 meters per second squared. Feel it almost as much as that person that ran into the concrete barriers the other day. Okay? They really felt it. All right? So 12 meters per second squared. Which direction is that?
Would it be west?
It would be. Is that important for the next steps?
Yes.
Yes. Okay? I have to make sure that I make that negative because this is positive. Okay? This is east. So my acceleration has to be 12 meters per second squared west. Now I can solve for D. Okay, manipulate for D. D will be VF squared minus VI squared divided by 2A. Right? And so that's going to look like this. 0 squared minus 24 squared divided by, oddly enough, negative 24. So 24 squared divided by 24 should be 24. I'm just thinking out loud. Yeah, pretty sure, right? Okay, so 24 squared divided by negative 24, okay? Sorry, it'll be 0 minus 24 squared, so I'm gonna have a negative number on the top divided by a negative number on the bottom, okay? And I'm gonna get 24.0 meters. Now, on that question, would I have to write east? How far do you skid? How far is distance, not displacement? On a test, I probably wouldn't mark it wrong if you wrote east, but it's not necessary because they did ask just for distance when they said how far. Okay?
What if on a test you wrote like the wrong, like if, let's say you said 24 meters west, but it doesn't require it's not vector, but you wrote the wrong direction, but it's not required? Would it still be?
I feel like I'd be more forgiving for the right direction when not required than the wrong direction when not required. Because I feel like that shows a different level of understanding. One's forgetful and the other's a bigger mistake. If that makes sense. Okay, so again, it's a challenging question, but not mathematically. And that theme, you are going to hear me say that so many times this unit. Oh, that question wasn't all that hard mathematically, but holy crap, did you have to sit there and think about it for a long time? Okay, that's what makes Newton's second law tricky. Okay, the math in this unit is actually some of the easiest math in the whole course. But man, oh man, do you have to be able to see into these questions, all right? Okay, here's another one. This one's really different. Okay, now, I'm gonna draw it for you, because that helps to be able to see it. Okay, and I want you to see if you can figure it out. Okay, so we've got a box on a horizontal frictionless surface, like this, okay? And it's 1 kilogram. There's a rope attached to it that's strung over a pulley. That's a pulley, by the way. Okay? Over that pulley is a 1.5 kilogram mass. Assuming this thing starts at rest, okay, what would be the acceleration of this box? I would say draw that diagram and see if you can identify any other forces that are acting there that might cause the system to move.
Are you able to find that video of the person driving through the barriers?
I didn't get welcomed into the group.
Oh.
Yeah, I asked for membership, and I still haven't heard anything, so I can't, I only saw it
It's very
because,
exclusive.
apparently it is, yeah. My wife's in the group, but apparently I'm not good enough, so I can see that. She's pretty great. Since the table is frictionless, the only force pulling on the 1 kilogram mass is the rope. Would you agree? Okay, so if the rope is the only thing that's pulling on the 1 kilogram mass, what's making the rope pull on the 1 kilogram mass?
Gravity?
Gravity. On the 1.5 kilogram mass. In fact, that is the only force acting in this entire system. Okay, so I can calculate that pretty quickly. Right? I'm just going to go Fg equals m times g. So I'll take my 1.5, okay, and multiply it by 9.81. All right, we got 14.715 newtons. Okay. If there are no other forces in that system, and there don't appear to be, that's also my what force?
Yeah.
It's also my net force. That's the vector sum of all forces right there. I didn't have to do any vector addition or do any tail to head stuff. I just had to look at that and go, well, that's the only thing that's there. Okay, and say F net equals 14.715 newtons. Now, that equals m times a. What mass do I use here?
2.5.
Right. Neither one of the boxes has a mass of 2.5 kilograms. But that 14.715 newtons is pulling both boxes. They're connected. They're what we call a system. The parts of the system have to accelerate together because the net force acts on them both. Right, so anytime you have a question where there's more than one mass and they are connected, they are a system, and the system's mass is the combined mass of all of its parts. So the acceleration of the 1 kilogram mass will be the same magnitude as the 1.5 kilogram mass. Right? They'll have a different direction because that one's going forward and that one's going down. Okay? But we'll still have 14.715 newtons, but now divided by the mass of the system. And when we do that, we get 5.9 meters per second squared. And since it's the 1 kilogram box that they're asking about, I should probably say forward, towards the pulley, along the table, basically anything that says, I realize that this is a vector quantity and it's going ahead. Okay, we're in the direction it's being pulled. Right? I'm gonna say this a million times, but was there any really difficult math in that question? No. Okay, rarely is there gonna be. Okay, the only time you're gonna have any significant amount of math is if you actually have to do any vector component addition in a question. That's the only time there'll be any significant math. Okay? All right, similar idea, but now it's what we call a vertical pulley. That's the situation you're dealing with now. Okay, see if you can do that one. Okay, let's have a look at this one. How many forces are in this system?
Two.
Force of gravity on each mass. They're hung over a vertical pulley. That means gravity is pulling down on each of them. So this one is going to be 14.715, 1.5 times 9.81. This one will be 19.62, 2 times 9.81. Right? Now, they're both acting the same direction. Is that okay? Well, they're actually not. Technically, they're both down, but they're opposing each other, right? The one mass is pulling on the other, and the other mass is pulling back on it in response. When we have something like this, what we can actually do is just say, I have 3.5 kilograms worth of mass in this system being pulled this way by 19.62 newtons, and this way by 14.715 newtons. That's really what's going on here. Because those two forces, even though they're both gravity and they both act down, are opposing one another. So now, can I calculate the net force? Since they are opposing each other, I do have to make one of them negative. So I'll have 19.62 minus 14.715, which should give me 4.905, I believe, newtons. Can I now calculate the acceleration of each box? And in fact, the acceleration of the system in general, because all of the parts of the system accelerate at the same rate. Maybe not necessarily in the same direction, but with the same magnitude at least, which is why we see one of those is positive 1.4 and one of them is negative 1.4. This box is going down, this box is going up. Okay, everybody all right with that? Okay. So when I do this final calculation though, I'm dividing by 3.5, the mass of the system. That is always true when we're dealing with a system of interconnected masses. All right, so that's kind of the new trick for today. We did some entry-level, basic Newton's second law problems, right? We started to build on that. Okay, again, contextually difficult, not mathematically difficult. Tomorrow's quiz is going to have questions like we worked on today, nothing terrible. Practice quiz is going to post, there'll be a video. Watch it all tonight. And tomorrow, we're going to move on to more complex system questions and maybe some vector stuff. That's where we're headed.